Hello everyone. This is the presentation of the public defense of my PhD thesis entitled Peer-to-Peer based grid support functions for smart inverters, distributed voltage and frequency control. In this presentation, I am going to present the main objective and the scope of the thesis, some basic concepts regarding voltage rise and voltage drop problems, and why we need to maintain voltage within maximum limit and minimum limit. Also, basic concepts regarding peer-to-peer control. Then I am going to present the main contribution of the thesis, the distributed optimization-based voltage control systems based on the dual decomposition and the alternating direction method of multipliers, the so-called ADMM, and then the policy-based distributed voltage control that has been implemented in the thesis to simplify the implementation of the dual decomposition and ADMM-based distributed voltage control systems, and then simultaneous provision of voltage and frequency control, finally conclusion and future work. Solar photovoltaic has experienced exponential growth in recent years. At the end of 2018, for example, the global photovoltaic capacity exceeded 500 gigawatt. This rapid growth of photovoltaic penetration helps the nations to fulfill their electrical energy needs without increasing fossil fuel consumption, which largely contributes to reducing greenhouse gas emissions and mitigating the climate change effect. Although photovoltaic systems are a key technology for implementing the shift towards a decarbonized energy supply, current distribution networks, the networks that deliver energy to our houses, were not designed to accommodate high photovoltaic generation. Consequently, grid operators are facing significant problems in controlling their distribution networks. And one of the main common problems is the voltage rise problem due to the reverse power flow from photovoltaic systems. This slide shows the traditional electrical power grid that consists of generation, transmission, and distribution. The thesis focuses on the distribution level of the grid, mainly on low voltage distribution networks. Since this presentation is intended for public audience, I would like to present some basic concepts regarding voltage rise and voltage drop problems, and why we need a control system to maintain voltage within maximum and minimum limits. But before doing so, I would like to mention the main objective of the thesis. The main objective of the thesis is to design and implement peer-to-peer based distributed voltage control algorithms that enable photovoltaic and photovoltaic battery systems to solve under voltage and over voltage issues of distribution networks. The thesis also aims to design and implement innovative control systems for photovoltaic battery systems to provide simultaneously multiple services, the so-called value stacking. We focus on combining distributed voltage control with a frequency containment reserve to increase value from photovoltaic battery systems. A typical photovoltaic system consists of solar panels, inverter, battery, and a net meter. Solar panels absorb sunlight and convert it into a direct current, DC current, using photoelectric effect. The inverter converts the DC current into an alternating current, AC, DC to AC. Behind the meter, battery energy storage system can be charged during the day when photovoltaic generation is high and discharged during the evening when the consumption is high. The net meter calculates how much energy is sent and received from the grid. Voltage drop. Let's start with this analogy. Electricity flows down your street a bit like water down a hose in your garden watering a row of trees via drippers. Your garden tap pushes water into the hose like your local transformer pushes electricity into the wires. Your transformer is a big device, probably up a pole somewhere in your street or around the corner. The tap supplies water at a high pressure, but as it progresses down the pipe, friction and offtake by drippers reduces this pressure to a low point at the final tree. The electrical equivalent of a pressure is voltage, which starts at a relatively high level, for example 250 volt at the transformer, and drops to a lower level at the final house. The drop in voltage down the line increases when houses are consuming more electricity. During evening, for instance, when everyone is cooking dinner, there is a risk that voltage at the final house may drop below the minimum allowed limit of 207 volt. Such low voltages are harsh on some voltage-sensitive appliances. Operating electrical equipment outside of its acceptable voltage rating can lead to premature equipment failure. Inductive loads, for example, like motors, can overheat because they consume more energy if they operate below their voltage rating, which shortens their life. To avoid voltage drop, the local electricity distributor needs to set the transformer to a relatively high voltage. However, if the distributor sets the transformer voltage too high, houses close to the transformer may sometimes experience voltage above the maximum allowed limit, which also risks damaging appliances. Most transformers at the distribution level cannot vary their voltage dynamically, so adjusting the transformer requires a truck visit and possibly a brief local blackout. Another solution can be to increase the size of the feeder, that is to reduce the overall resistance on the entire network, and if you reduce the resistance, then you reduce the voltage drop. Another solution can be to use an active element such as capacitor banks at the substation where the main transformer is located. On top of the voltage drop problem, solar systems pose additional challenge to the Distributors Voltage Regulation Act. The new challenge is the voltage rise problem. While solar voltage rise is a relatively new problem, the opposite problem, voltage drop, has been well known since Thomas Edison lit up in New York City streets. When your solar system is producing more power than your home is using, it sends the excess back to the grid. In order for power to flow from your home to the grid, the voltage from the solar inverter has to produce a voltage that is a couple of volts higher than the grid voltage. The problem arises when, for example, half the people on your street have solar systems too. Every system is lifting the grid voltage at the same time. Then the voltage will keep getting higher and higher. This increases the chance that some households will exceed the maximum allowed voltage, especially around midday on a sunny weekday with high generation and low consumption. Why should we care about voltage rise? When high voltage is consistent, more current will flow through the electrical appliances. When this high voltage is consistent, and thus the high current is consistent, it may lead to burning of electrical appliances. If it doesn't burn, it will lead to consuming more electricity. Another important issue is inverter cycling on and off. Let's assume the following case, that it is a sunny summer day and all the solar inverters on your street are running at maximum production. As a result, the voltage output of your inverter gets higher than the maximum allowed limit, which is 253 volt. Your inverter injects 5 kilowatt to the grid. Now, after a few minutes, the inverter will disconnect to protect itself from the overvoltage. And most probably, the inverters of your neighbors will disconnect as well to protect themselves from overvoltage. Now, due to this, the reverse power flow will reduce and the voltage will drop below the maximum limit, 253 volt. Now the inverters will think that there is no problem, and then they will connect again, and your inverter will inject 5 kilowatt again to the grid. Then the voltage will get higher than 253 volt, and the inverter will disconnect to protect itself. So your inverter will keep disconnecting, connecting, disconnecting, connecting. If the inverter spends the lunchtime cycling on and off and reaching high voltages, then your inverter won't last long. Your inverter won't last long. Also, when the inverter is off, your solar system is not generating energy. And when your solar system is not generating energy, you are losing money. I hope it's now clear what is voltage rise and voltage drop problem, and why it is important to have a control system or some active elements to control voltage between maximum and minimum limits. Solutions to solve the voltage rise and voltage drop problems can be classified according to the following 3 categories. Solutions that are implemented within the grid operator infrastructure, such as network reinforcement, for example, increasing the size of the feeder to reduce the total resistance of the network, that is to reduce the voltage drop. On-load tap changer, that is to change the voltage of the transformer dynamically. Storage owned by the distribution system operators that can be charged during the day when the photovoltaic generation is high, and it can be discharged during the evening when the consumption is high. Network reconfiguration, it is something like, let's say there is a high reverse power flow in phase A and low reverse power flow in phase B and phase C. What you can do is that you use a normally open switch, you close it and you let part of the current flows from phase A to phase B and phase C. That is to reduce the high reverse power flow in phase A. That is to mitigate voltage rise in phase A. The second category, solutions which are implemented within the prosumer infrastructure, such as behind-the-meter battery energy storage systems, curtailing the photovoltaic generation, and reactive power control provided by the inverters. The third category, solutions that are implemented within the grid operator's infrastructure and the prosumer infrastructure. The thesis focuses on the second category. Mainly, we use the photovoltaic inverters and photovoltaic battery inverters to solve the voltage problems. Photovoltaic inverters and photovoltaic battery inverters can participate in voltage control by expanding their features with added grid voltage support functions and without major hardware modifications. Grid voltage support functions, they can absorb reactive power to mitigate voltage rise or inject reactive power to mitigate voltage drop. They can also curtail photovoltaic power to mitigate voltage rise. Also charge the battery during during photovoltaic peak period to mitigate voltage rise, and discharge it during demand peak period to mitigate voltage drop. Photovoltaic battery inverters can also discharge batteries in response to frequency deviations to participate in frequency control. This is the outline of the thesis. The thesis consists of 7 chapters. 5 main chapters plus the introduction and conclusion. In chapter 2, a peer-to-peer based control paradigm is proposed for controlling the distribution grid. Chapter 2 creates a framework for the rest of the chapters. In chapter 3, peer-to-peer based voltage control algorithms are developed based on distributed optimization techniques. The work of chapter 3 is validated experimentally in chapter 4. The work of chapter 5 is motivated by the complex implementation of the distributed optimization algorithms applied in chapter 3. In chapter 5, a novel control methodology is proposed to implement a distributed voltage control system. The methodology is based on robust optimization techniques and linear decision rules. The robust optimization problem developed in Chapter 5 is extended in Chapter 6 to enable the photovoltaic battery systems to provide simultaneously voltage and frequency control. We are happy that we managed to publish all the contents of the thesis in 5 journal papers and 2 conference papers. As I mentioned, inverters can participate in voltage control by expanding their features with added grid voltage support functions. The control algorithms of the grid voltage support functions can be designed mainly based on centralized control, communicationless local control, and peer-to-peer based distributed control. Generally speaking, centralized voltage control systems have poor reliability and scalability. Local voltage control systems suffer from degraded performance. And to overcome the drawbacks of centralized voltage control systems and local voltage control systems, the thesis implements peer-to-peer based distributed voltage control algorithms. Peer-to-peer control enables the inverters to communicate with each other in a peer-to-peer fashion. And with communication, they are able to overcome the absence of the centralized controller and distribute a centralized problem into several sub-problems that can be solved locally. Peer-to-peer communication and peer-to-peer control enable the inverters to make the correct control decision in every particular situation to maintain voltage at any node in the network within allowed limits. Such a control system has many advantages. For instance, failure of one agent or one inverter doesn't disable the entire control system as in the centralized controller. In the centralized control system, there is only one unit doing everything, and failure of this unit disables the entire control system. Also, the peer-to-peer control is more scalable, and maintenance in peer-to-peer control doesn't require a complete shutdown of the entire control system as in the centralized controller. Future distribution networks are expected to accommodate thousands of distributed energy resources. Communication of grid operators with every system is in a centralized way is out of reach, complex, and very expensive. To reduce this complexity, the thesis proposes to decompose the grid into microgrids, coupled microgrid. And in each microgrid, a peer-to-peer control can be carried out. On a higher level, the microgrids can be coordinated in a peer-to-peer fashion as well to ensure overall system stability. And the coordination can be via coupling agents. Such a coupling agent can be a digital substation, for instance. The thesis contributes to this paradigm by designing grid voltage and frequency support functions that enable photovoltaic and photovoltaic battery inverters to carry out a distributed voltage control in each microgrid and to participate in supporting the grid frequency. Control algorithms of the distributed voltage control systems in literature are mainly based on the dual decomposition and the alternating direction method of multipliers, the so-called ADMM. The dual decomposition and ADMM are iterative decomposition algorithms. Therefore, one of the main challenges in using them to implement a distributed voltage control is the speed of convergence. Convergence should be reached within a reasonable time to make these algorithms suitable for implementing a real-time distributed voltage control system. For instance, it doesn't make sense to wait 1 hour to solve a single voltage problem in real time. The basic concept of the dual decomposition and the ADMM is based on the gradient descent, or the opposite algorithm, gradient ascent. Gradient descent is an optimization algorithm used to minimize some function by iteratively moving in the direction of steepest descent, that is, as defined by the negative of the gradient. To understand the gradient descent, the best analogy, in my opinion, is one about hiking mountains. Let's assume that you are at the very top of Mountain Everest and you need to work your way down to the bottom. You start by looking for a path that takes you to a lower point and you follow it. But still, you aren't at the bottom. So what you do the exact same thing. You look for a path that takes you to a lower point and you follow it. You keep doing so till you reach the bottom. You look for a path that takes you to a lower point and then you follow it. It takes a while, but eventually you reach the bottom of the mountain. The mathematical equivalent of looking for a path to a lower point is the negative of the gradient. And the number of steps you need to move from the bottom to the, from the top to the bottom is equivalent to the number of iterations that dual decomposition and ADMM need to solve a single voltage problem. Working your way down from the top to the bottom is like minimizing the cost of operating the voltage control system, or minimizing the cost of the active power and reactive power needed to maintain voltage within maximum and minimum limit. The first iterative decomposition algorithm the thesis discusses and implements is the dual decomposition. The dual decomposition is based on the Lagrangian relaxation and the dual ascent method. The dual ascent method has the same principle as the gradient descent, but it's opposite, like moving from the bottom to the top. Lagrangian relaxation converts a coupled optimization problem into a decomposable one by transferring the complicating constraints to the objective function. The complicating constraints couple the optimization problem. And if you include them in the objective function, you will be able to decompose the problem into several sub-problems that can be solved locally, considering the peer-to-peer data interchange between the agents or the inverter. The main drawback of the dual decomposition is that it has slow speed of convergence. The thesis studies the convergence speed of the dual decomposition-based voltage control system to see to which extent the number of inverters participating in such a system can be extended. Results show that dual decomposition can be used to implement a distributed voltage control system with a few agents. I would like to point out that if you increase the number of agents in iterative decomposition algorithms, then you need more iterations to converge. An effective iterative decomposition algorithm that enjoys fast rate of convergence is the ADMM. The ADMM utilizes the augmented Lagrangian function that incorporates a quadratic penalty of the complicating constraints. State-of-the-art ADMM is a sequential two-block system. One of the main findings in the thesis is that the direct extension of the two-block ADMM into parallel multi-block ADMM, the so-called Jacobi ADMM, without additional assumptions or modifications, slows down the convergence significantly. The so-called Jacobi ADMM is even slower than the dual decomposition. I spent quite a lot of time trying to find a solution to accelerate the convergence of the parallel multi-block ADMM. I found out that including proximal terms in the augmented Lagrangian functions, as here, and updating or modifying the update of the Lagrangian multipliers by multiplying the augmented penalty factor by an acceleration factor. This speeds up the convergence significantly. This method is called the Jacobi proximal ADMM. It has been invented in 2017, and the thesis applies this method to design and implement a real-time distributed optimization-based voltage control algorithm that enjoys fast rate of convergence. This slide shows a comparison between the dual decomposition Jacobi ADMM and the Jacobi proximal ADMM. It's clear from this figure that the Jacobi proximal ADMM is much faster than the dual decomposition and the Jacobi ADMM, and that the Jacobi ADMM is slower than the dual decomposition. We have tested the results of the real-time distributed optimization-based voltage control algorithms experimentally by building a kind of peer-to-peer based microgrid that consists of 4 layers: the hardware layer, the control layer, the communication layer, and the monitoring layer. The hardware layer consists of programmable inverters and the programmable DC power supply. The programmable inverters and the programmable DC power supply are used to emulate a photovoltaic system. The control layer consists of the control loops of the inverters and the grid voltage support functions. The communication layer consists of device-to-device communication modules that are used to enable peer-to-peer communications between the agents, and the monitoring layer or the data acquisition. It's the layer where we see the results of the experiments. As I mentioned, we use device-to-device communication modules to enable peer-to-peer communication between the inverters or the agents. The device-to-device communication modules are based on LoRaWAN technology. They have been built and supplied by Center for Wireless Communications, University of Oulu in Finland. So I would like to thank them for helping us. Despite the advantages of the dual decomposition and the ADMM, their implementation is complex. The main problem is their sensitivity to step size parameter and the penalty parameters. Inappropriate settings of these parameters degrade the performance significantly. Tuning these parameters require several experiments of a trial and error. Also, implementing a distributed voltage control system using the dual decomposition and ADMM requires solving a complex optimization problem every iteration. For example, every 5 seconds. The complex implementation of the dual decomposition and ADMM based voltage control systems motivated us to find another control methodology to implement the distributed voltage control system. Therefore, we propose to coordinate the inverters offline on a day-ahead basis by computing a set of linear control policies. The idea is to simplify the implementation of the real-time distributed voltage control by letting the the grid voltage support functions solve in real time a set of linear equations rather than solving a complex optimization problem. Polyhedral uncertainty set is used to model uncertainties in the household demand and PV generation. The thesis applies robust optimization to optimize the coefficients of the linear policies and to find solutions that remain feasible for any realization of the uncertain data in a predefined uncertainty set. Also, the main reason for using the robust optimization and not the stochastic optimization is that if we use the stochastic optimization to obtain robust solution, then we need thousands and thousands of scenarios, and then it will take a lot of time to solve the optimization problem. Whereas in robust optimization, you just need to model one scenario, and this scenario, it is not the worst case scenario, because in robust optimization, you can use the so-called budget of uncertainty. For instance, at let's say 6 a.m., you won't let your photovoltaic generation or the uncertain photovoltaic generation varies between maximum and minimum, because you know that the generation will be zero. So at 6 a.m., what you do is that you set the budget to zero. So we used budget of uncertainty together with robust optimization, and only one scenario to obtain robust solution, and also to obtain a solution that is not too conservative. It is conservative, but it is not too conservative. That is the message. When battery energy storage systems are used to provide only one surface, such as voltage control, they are inactive or partially used most of the time. Their unused capacity could be used to provide other surfaces, allowing them to generate additional revenues. Hence, there is a need for designing innovative control systems that enable battery energy storage systems to provide simultaneously multiple surfaces, the so-called value stacking. Since frequency control has been identified as one of the most or as one of the highest value surfaces for battery energy storage systems, we are interested in combining distributed voltage control with frequency control. There is another motivation behind combining voltage control with frequency control. That is, providing frequency control with photovoltaic battery systems connected to low voltage distribution grid can lead to voltage issues. In order to mitigate these issues, part of the reserve capacity of the photovoltaic battery systems should be dedicated to solve voltage problems caused by their surfaces. In my opinion, grid operators should require frequency control providers with photovoltaic battery systems located in distribution network to provide frequency control simultaneously with voltage control. To this end, the thesis develops a novel, robust control methodology that enables photovoltaic battery systems to provide simultaneously voltage control and frequency control. The system consists of two phases, offline and real-time. In the offline phase, we run a robust optimization problem to calculate linear voltage control policies and linear energy management policy. Why we need an energy management policy for a battery with limited capacity providing a frequency containment reserve? This is because the frequency signal has non-zero mean over short period. Also because of the self-discharge of the battery. So the message is, if you would like to use a battery energy storage system to provide a frequency containment reserve, you do need an energy management policy so that you are able to provide frequency containment reserve continuously, and you would have 100% availability of the surface. Otherwise, your battery will be fully charged or fully discharged within a few hours. This is very important. In real time, the inverter consists of a grid voltage support function that applies the linear voltage control policies. Of course, the grid voltage support function has to communicate with other inverters because each policy is based on the power injection of the control nodes and the power injection of the other control nodes. The frequency support function calculates the power of the frequency containment reserve and also applies the energy management policy to maintain the energy content of the battery within limits while providing frequency control. Another thing in the thesis, which is novel, is that we divide each battery into 3 virtual batteries, one related to voltage control battery that calculates the or control the voltage together with the inverter reactive power, or a battery that participate in upward frequency regulation, and RDN battery that participate in downward frequency regulation. Why we have a dedicated virtual battery for the upward frequency regulation and another one for the downward frequency regulation? Because in distribution networks with the high photovoltaic penetration, sometimes you cannot, for instance, respond to the upward frequency regulation. For instance, during midday, when you have a voltage rise, you cannot discharge the batteries to respond to the upward frequency regulation, because this will make the voltage rise problem even worse. But you can respond to the downward frequency regulation, because this will help to mitigate the voltage rise problem. Regarding the conclusion, I would like to mention the main contributions of the thesis. The first contribution is proposing a high-level functional architecture for peer-to-peer based control paradigm of distribution networks. The second one, implementation of a novel, fast, real-time optimization-based distributed voltage control algorithm, and the development of a multi-layer, multi-agent, peer-to-peer based voltage control test bed. The implementation of a novel policy-based distributed voltage control algorithm, and finally, the implementation of a novel control methodology for photovoltaic battery systems to provide simultaneously voltage control and the frequency containment reserve. Regarding the future work, we have tested most or all the algorithms of the thesis, assuming perfect communication and correct data. However, in reality, you would have communication failures and delays and also incorrect data. Therefore, we recommend for future work to test the performance of the algorithms under communication failures and delays and with incorrect data, and to come up with solutions to cope with these issues. In the thesis, we focus on balanced distribution networks. In reality, distribution networks, they are unbalanced. So we recommend for future work to modify the algorithms so that you can use them to control voltage of unbalanced low voltage distribution networks. To be honest, it is easy to do this. You just need to apply the same algorithm but per phase. Distribution networks with incomplete data, the algorithms implemented in the thesis, they rely on the so-called voltage sensitivities that we calculate using the resistance and reactance of the distribution feeder. In reality, distribution system operators, they don't have complete knowledge of their distribution feeders, so you won't be able to know all the resistances and reactances of the distribution feeders. It would be nice to combine the algorithms with the machine learning algorithms to learn the voltage sensitivities or to estimate the impedance of the feeder. Voltage regulation market, currently there's no market for peer-to-peer voltage control, hence it is recommended for future work and to be honest, it's highly recommended for future work to work on business models and design and market design for peer-to-peer voltage control, because even if you have the technology, you need a market for it to be able to use it. Finally, the validation in real-life applications. I have tested the results of the real-time distributed optimization-based voltage control algorithms in a laboratory environment. We know that test conditions in real-life applications may vary. That's why it is recommended, if possible, for future work to test the algorithms in real-life applications. We have published all the contents of the thesis in 5 journal papers and 2 conference papers. I also contributed to 3 other conference papers. The thesis is online. You can just Google it and you can download it. It's open access. And before saying thank you, I would like to thank my supervisor, Professor Geert de Koning, for the continuous support and motivation. Geert, your guidance helped me a lot in all the time of research and writing of the thesis. I couldn't have imagined having a better supervisor for my PhD thesis. I also would like to thank FWO for granting me a PhD scholarship. I would like to thank all the members of the examination committee. I would like to thank the chairman for chairing the committee, and Professor Johan Driesen and Professor Johan Soykens for being part of my supervisory committee throughout the years. Thank you, Professor Raphael Kerr and Professor Wu, for being part of the jury and for the useful remarks that have definitely made the thesis more complete. I am also very grateful to the lab technicians Johan, Luc and Geert for assisting me in the experimental works. I would like to thank Kathleen, Katya, Verli and Veronica. They have eased my life by fixing the administrative, financial and ICT problems. Of course, I would like to thank all my colleagues and ex-colleagues at Electa and Energyville for making my PhD journey the most memorable one. I owe special thanks to Jonas Engels, Sander Kleis and Mudar Abedrabbo. Thank you all for following this presentation. And last but not least, I would like to thank my family, my parents and my wife for supporting me throughout this journey. Thank you.